Welcome to the intersection of mathematics and the quantum world. In this episode, we dive into a fundamental aspect of quantum mechanics, linear algebra. Join us as we explore how linear algebra is not just a tool, but the very language that describes quantum states and operators, forming the backbone of our understanding of the quantum universe. Quantum mechanics, the branch of physics that deals with the behavior of particles at the atomic and subatomic levels, is rich in complexity and counterintuitive phenomena. To navigate this world, scientists use the precise and elegant language of linear algebra. Linear algebra, a branch of mathematics dealing with vectors and matrices, provides the framework necessary to describe and manipulate quantum states. In quantum mechanics, the state of a particle is represented by a vector known as a state vector in a complex vector space. This space, often referred to as Hilbert space, is where all possible states of a quantum system live. Unlike classical states, which can be described with simple numbers like position and velocity, quantum states require the full power of vector representation to capture their probabilistic nature. Hilbert space, the stage on which quantum mechanics plays out, is a space of infinite dimensions. Each dimension corresponds to a possible state of the quantum system. For example, in the case of a spin-2 particle like an electron, the Hilbert space is two-dimensional, corresponding to the up and down spin states. Understanding the structure and properties of Hilbert spaces is crucial for grasping the behavior of quantum systems. In linear algebra, operations performed on vectors are represented by matrices. In quantum mechanics, physical observables like momentum, position, and spin are represented by operators, which are mathematically matrices. These operators act on state vectors, transforming them in ways that correspond to physical processes or measurements. One of the key concepts in linear algebra and quantum mechanics is that of eigenvalues and eigenvectors. When a quantum observable, represented by an operator, acts on a state vector, the result is generally another state vector. However, in some cases, the result is the same state vector multiplied by a scalar. This scalar is the eigenvalue, and the state vector is the eigenvector. Eigenvalues represent the measurable values of the observable, such as the energy levels of an atom. Quantum superposition, a principle where a quantum system can be in multiple states simultaneously, is also described using linear algebra. A superposed state is a linear combination of basis vectors, each representing a possible state of the system. The coefficients of these combinations are complex numbers that determine the probability amplitude of each state. Quantum mechanics uses a unique notation known as Bra-Ket or Dirac notation, specifically tailored for the linear algebraic structure of quantum theory. In this notation, state vectors, kets, and their dual vectors, bras, provide a concise way to represent quantum states and the inner products between them, essential for calculating probabilities and expectations in quantum theory. Having explored the fundamental concepts of linear algebra and quantum mechanics, let's now turn our attention to its practical applications and the profound implications it has in understanding quantum phenomena. Linear algebra isn't just a mathematical abstraction. It's a vital tool that physicists use to unravel the mysteries of the quantum world. Matrix mechanics, one of the earliest formulations of quantum mechanics, uses matrices to represent quantum states and operators. The evolution of a quantum system over time, for instance, can be described by the Schrödinger equation, which in matrix form relates the time derivative of the state vector to the Hamiltonian operator of the system. This operator, representing the total energy of the system, is a key concept in understanding quantum dynamics. In quantum mechanics, measurement is a process that yields a definite outcome from a range of possibilities described by a quantum state. Linear algebra describes this through projection operators. These operators act on a state vector, projecting it onto a subspace corresponding to a particular measurement outcome. Understanding these concepts is crucial for interpreting quantum experiments and predictions. Quantum entanglement, a phenomenon where quantum states of two or more particles are interconnected, can also be understood through linear algebra. The joint state of entangled particles is described using tensor products of individual state vectors. This mathematical representation helps in studying the properties and implications of entangled systems, which are central to quantum information theory and quantum computing. Quantum systems are often in mixed states rather than pure states, especially when part of the system is unknown or interacting with an environment. Density matrices, which are a generalization of state vectors, are used to represent such mixed states. They provide a powerful linear algebraic tool to study statistical mixtures of quantum states, essential in quantum statistical mechanics and open quantum systems. Linear algebra finds significant applications in the realm of quantum computing. Quantum algorithms, such as Shor's algorithm for factoring large numbers, rely on the manipulation of qubits represented by state vectors and operated on by matrices. Understanding the linear algebra behind these operations is key to appreciating how quantum computers can solve complex problems much faster than classical computers. While linear algebra provides a robust framework for quantum mechanics, challenges remain. Bridging the gap between the abstract mathematical world and the experimental realities of quantum systems is an ongoing endeavor. As quantum technologies advance, so too will the applications and understanding of linear algebra in this context, potentially uncovering new aspects of quantum theory and its relationship with the broader universe. In conclusion, linear algebra is more than just a mathematical tool in quantum mechanics. It is the language that describes and predicts the behavior of the quantum world. From the smallest particles to the vast complexities of quantum computing and information, linear algebra remains a fundamental aspect of quantum theory. As we continue to probe the depths of quantum mechanics, the power and elegance of linear algebra will undoubtedly play a central role in unveiling the mysteries of the quantum universe. This was an experiment to see if anyone wanted some videos that go a bit in the depth of subjects so that the mathematics have to be applied to the theories. It was a very surface view, and I will probably make some videos that goes into depth of mathematics behind entanglement, for example. I want to make it so you don't need to have a math background to understand most things. So if you liked the video, please give it a thumbs up and comment below. Also, if you are new, please follow if you like the video.